Not long ago, in a galaxy that you actually live in, you decided to learn astronomy. And one of the things that you wanted to learn about were galaxies. So here is an artist's view of our Milky Way galaxy. So whenever you see a picture like this, and it says, oh, there's the Milky Way galaxy, it's going to be an artist's view because no human-made cameras have gone far enough away to take a picture like this. You can see some of the different aspects of the galaxy. The disk, so that's the sort of that edge-on part. There's that circular bulge, or also sometimes called the core of the galaxy. The halo, so stars and globular clusters that kind of orbit around that bulge. The Milky Way galaxy is about 100,000 light years across. So a flashlight that is turned on right here will reach the other side of the galaxy in about 100,000 years. You can see the sun here is about a third of the way out from the bulge to the disk. So if you want to think of that as a scale, take one of your old CDs and then take an old ping pong ball, cut it in half, and glue the top half to the middle of the top of the CD, the bottom half to the middle of the bottom of the CD, and that's a reasonable scale representation of the Milky Way galaxy with the CD thickness and the ping pong ball in its relationship. The CD might be a little bit too thin, but it's close. Here's just a rendition. We think of the galaxy as something static, just some collection of stars, like you take some salt out of a cup and you pour it down on the table and it just sits there. But the stars in the galaxy don't just sit there. They orbit the center of the Milky Way, and the sun takes about 200 million years to orbit the center of the Milky Way. And they don't go in a perfectly flat plane. They kind of take this sort of like a fish or mermaids gliding through the water, sort of jumping out of the water, jumping into the water. But this trip around is what takes about 200 million years. Stars, and so the sun would be represented by one of these yellow lines here. Stars in the halo and globular clusters, they orbit more irregularly, circular around the bulge, but they don't do any sort of fancy weaving in and out. And the stars near the center of the Milky Way, they're much more chaotically moving around because they are influenced significantly by the supermassive black hole that's in the center of our galaxy. So galaxy formation, you remember the circle of life from The Lion King, and also talking about stars. There's sort of a circle of life with galaxies and stars as well, and that thing is called the star gas star cycle. And since it's a cycle, it could start anywhere. But let's just start with this atomic hydrogen clouds. So the very first substances in the universe were hydrogen and helium. So essentially atomic hydrogen. Those particles will form heavier particles, still in the cloud though, so molecular clouds. Those molecular clouds aren't perfectly evenly distributed in terms of their mass. Some parts are a little bit more densely packed together, some less densely packed together. The more densely packed together regions are going to form stars and solar systems, and that's then where the galaxies will form. Those stars go through middle age, fairly stable. They age. Stars that are about the mass of the sun will become planetary nebulas. Their outer layers will slowly poof out. Larger mass stars will go supernova and violently push most of the material in the outer part into outer space. That material seeds the formation of future stars, and then the cycle continues. We didn't really know a lot of this stuff about galaxies until we started studying the galaxy in different wavelengths. So the one that you're most common with, of course, is the visible wavelength. So that's what we see when we look with the naked eye, or we just take pictures with film, well, which most people don't do anymore, or even just regular old digital cameras. The next wavelengths that were used were radio waves, and you can see the galaxy looks a lot different in radio waves than it does in visible light. And there are different wavelengths of radio waves as well. So radio is a huge chunk of the electromagnetic spectrum. Infrared radiation. Infrared radiation is a great way to see clouds of gas and dust. So you can see how the center of the Milky Way is super bright because there's a lot of clouds of gas and dust there, and those are being heated up by all the stars that are between us and the very center of the galaxy. So if you look towards the constellations Sagittarius and Scorpius, that's the thick part of the Milky Way galaxy. Even in the visible spectrum, you can see it's much more densely populated. If you could see in the infrared, even more so. And then the higher energy wavelengths as well, X-ray and gamma ray. You can see there some sort of hot spots that you don't see in the visible. So, it's blank right there. Those are regions where there are highly energetic transactions going on, typically with young stars. Young stars radiate a lot more in the high energy end of the spectrum, as do blue stars. Blue stars are shorter lived stars, so even though they might be far along in their life, they are much closer to the beginning of their life, and they're burning hot throughout their life. Here again is a galaxy. This is not the Milky Way, but it's a galaxy similar to the Milky Way. And this shows the star formation, and it also shows a little bit, you kind of get this sense of motion here. And people think the spiral arms move kind of like a pinwheel, but the arms themselves don't move. The spiral galaxy actually consists of what are called density waves. So places where there's a high density region of material and a low density region of material. And the stars, for the most part, and the gas and the dust move through those density waves, but the density waves themselves don't move. So think of you are driving along, and so lots of cars are driving along, and there's an accident on the other side. Well, people are driving, and then they get to the accident, and they kind of go slow near the accident, but then they get past the accident, and they move fast again. Anybody who's sitting and watching, whether it's different cars, so then different cars come by, and the backup stays in the same place, even though it's always different cars that are going through that backup. So the spiral arms stay in the same place, even though there are different stars that are passing through that spiral arm. Within the spiral arm, you can see a lot of different structures. The light blue structures here, those are new stars that are forming. The red structures, those are clouds that are actually being ionized or energized by the new stars that are being obscured by them. This dark region here is where gas clouds are basically colliding with each other and getting more dense. And let's see how this works here. I thought I could start a video that would actually show it, but I couldn't get it to work. Here's the story of galaxy formation, just in 4 images. So we've got this cloud of gas and dust that's forming. It's not perfectly uniform, so there are some spots that are slightly more dense than others. And those clouds, those dense spots form, and those are the oldest stars. So the oldest stars, they're of course forming throughout, but within the middle here, that's where the cloud, just like with the formation of the solar system, in the middle, you've got the greatest density of material. So it's going to start to collapse down towards the middle and start to rotate. So you get continual star formation out here. There isn't as much gas and dust then in the outer region to continually forming stars. So stars that are in the halo, they're the oldest stars. And new stars don't form very often in the halo. They form the most in the disk. And then after billions of years or so, most of the clouds, the sort of the loose material here, has formed into stars. And then it's the cloud that's in the plane of the disk that, as it passes through the density waves, will form new stars. Here's something called the Hubble Deep Field. It's a tiny, tiny part of the sky. Imagine setting down a tennis ball at one end of the soccer field, going to the other end and looking at that tennis ball. The area that tennis ball seems to take up, that's how big the Hubble Deep Field is. And all these, the vast majority of these things are galaxies. The only things in this image that aren't galaxies are the few items that have the lines that radiate out from them. Those are stars. The vast majority of things here, and there are a couple more stars in here, but the vast majority are galaxies. There are different types of galaxies. The two main types of galaxies are spiral galaxies and elliptical galaxies. There are two types of spiral galaxies: barred spiral galaxies, so they have that flat bar in the middle, so the core is sort of elongated, and then non-barred, like this. And the Milky Way is a barred spiral, and these letters just correspond to how long the bar is compared to the actual bulge itself. How different types of galaxies come to be, there are two main ideas. One is that they formed that way. So in clouds that were a little bit more diffuse and uniform, there wasn't this central area to form the bulge, so that those are elliptical galaxies. The second model is when elliptical galaxies collide, when spiral galaxies collide, they form elliptical galaxies. So one idea is that elliptical galaxies were formed from the beginning. The second is that they're a combination of spiral galaxies. Most likely, both of those methods are influencing elliptical galaxy formation. Here's just a computer model of galaxies colliding. So two spiral galaxies colliding. They collide with each other. And by the way, when galaxies collide, there are very few star-star collisions. The Andromeda Galaxy and the Milky Way Galaxy are heading towards each other, and they will collide well into the distant future. But when they collide, they're not going to have all the stars bump into each other like that. The stars will pass through each other, but then they'll start to oscillate back and forth like this. Some stars will be flung out in the collision, and what will result here is this sort of irregular elliptical shaped galaxy. So sometimes it's irregular. Over a long period of time, the irregularities would mask out and we would end up with an elliptical galaxy. You might say, well, that's a computer model. How do we know that's going to happen? We've actually seen it happen. Not while it's happening, because it takes millions of years, but the end result of that. So two spiral galaxies collided, and then here are the arms that are shooting out. And in this collision region, notice there are lots of these blue regions, so new stars have been forming. Evidence that there is a supermassive black hole in the middle of the Milky Way. Taking an image, being able to look through all the infrared light, taking pictures over about a 20-year period, these stars seem to move, and it looks like they're orbiting a common center. And based on their motion, we can determine the size of that supermassive black hole. It's about 4 million solar masses. And these stars are all within a fairly small area, 1,600 astronomical units. That's 1,600 times the distance between the Earth and the Sun. That is about maybe 4 times the distance between the Sun and Pluto. So a very small region of the sky. Here's an image of that. X-ray flare. Because the center of the Milky Way, there's so many stars, there's so much going on there, it's a much more highly energetic region than near where we are. So it would be much dangerous. It's unlikely that there's life similar to ours on planets orbiting stars near the center of the Milky Way. Here is another galaxy. Oftentimes those supermassive black holes shoot out particles in a jet. More evidence of that. Even if we can't see what's going on, we can't see the stars, like it would be difficult to see the stars near the core of another spiral galaxy, we can look at the spectra. So as there's this rotation here, the side of the galactic nucleus that's moving towards us is going to be blue shifted. The side that's moving away from us is going to be red shifted.